the break where we said that we saw how you can estimate the pKa of a weak acid from a titration curve of that weak acid with a strong base like hydroxide. And we saw that if you measure the volume that you need to get to the equivalence point and then go back halfway to the start, then the pH at that point in your titration will be the same as the pKa of the weak acid that you're using, right? The other thing that we can say from that, and this is what was alluded to by my friend at the back at the time, was that the fact that that's the flat part of the curve gives you an indication about the fact that any buffer solution that you might make using a particular weak acid and its conjugate base will always have a pH that's quite close to the pKa of that weak acid. It might not be exactly if the amounts of the weak acid and the conjugate base aren't exactly the same, but it'll be close to the pKa, right? And so what that means is that if you want to make a buffer of a particular pH for some experiment that you want to run, then you have a whole bunch of different weak acids that you could choose from. There's ethanoic acid, but there's formic acid, there's benzoic acid, there's malonic acid, there's a whole bunch of different ones you could choose. And so the way to work out which weak acid might be best for the buffer solution you want is to look for what pH you want that buffer solution to be at and then match that up with a weak acid that has a very similar pKa value. Right? So you can look up in books what the pKa's of the different weak acids are. And so, for example, if you wanted to prepare a buffer solution with a pH of about 4.5 and you had on the shelf two weak acids, one of which had a pKa of 4.6 and the other had a pKa of 5.9, then you would go with the weak acid that had a pKa of 4.6, right? That's going to be very easy to use to make a buffer with a pH of 4.5, whereas the other one's going to be much more difficult. Okay, so now we move on to another question. Well, actually, it's another part of the same question, to be honest, and then there's a third question. So what about if we added 12 mils of 0.100 moles per litre sodium hydroxide to 20 mils of 0.100 moles per litre ethanoic acid? Right, so the previous problem we did, we added 10 mils. Now what about if we add 12? This is going to make the numbers all a bit more interesting, yeah? Okay. So again, what we're going to do is we're going to calculate the amounts of the weak acid and the hydroxide ions before we mix the solutions together, and then we calculate the amounts after the reaction has happened. And so initially we work out these amounts using the amount is equal to the concentration times the volume, like we did before. And so we can work out that the amount of the ethanoic acid is the same as it was before, 2 times 10 to the minus 3 moles. But now the amount of hydroxide is a little bit different. It comes out as being 1.2 times 10 to the minus 3. And so what we're going to do then is we're going to do the same thing, yeah? So what I'm going to do is let you sit and have a go at doing that table, right? So it's just like we did before. You write out the equation, and then you write before the reaction, and then underneath each of the species, you write down the amounts of everything, and then you put after reaction, and you write down the amounts of everything as well. Okay, so have a go at doing that, and then we'll move on to the next slide, and you can see it. With those amounts that we just worked out using those little calculations previously. And then the second line, again, because it's the limiting reactant, the hydroxide is going to end up being 0. It all gets used up when the reaction's finished. The amount of the ethanoic acid that's left over will be the amount that you started with minus the amount that reacted. And the amount that reacted will be the same as the amount of hydroxide ions that reacted because of that 1-to-1 balancing. And so hopefully you can see that it's going to be 0.8 times 10 to the negative 3. That's just 2 times 10 to the minus 3 minus 1.2, the amount that reacted. And then the amount of ethanoate that's produced by the reaction will be the same as the amount of hydroxide that reacted, again because of that 1-to-1 ratio. And so if 1.2 times 10 to the minus 3 moles of hydroxide reacts, you should make 1.2 times 10 to the minus 3 moles of ethanoate as the product. Okay, so now we've got those numbers. We can pop them into our equation. And now it's a little bit different because now those numbers that log term doesn't all just disappear. So pH is equal to the pKa plus the log of the amount of the conjugate base over the amount of the acid. It's important to get the numbers around the right way, yeah? So the amount of conjugate base, the amount of ethanoate that we've just worked out is 1.2 times 10 to the negative 3. The amount of the weak acid is 0.8 times 10 to the minus 3. That's how much of that was left over after the reaction. And the log of that ratio comes out as being 0.18. And so now the pH is 4.76 plus 0.18, which is 4.94. Okay? And so that'll correspond to point D. Does it say this? No. Point D, if you like, on our W curve. We've added a little bit more hydroxide, so we're a little bit further through in the titration, and so the pH has gone up a little bit. Yeah?
Why was it 0 milliliters of the
Initially, because it's a product of the reaction, and before you do the reaction, there's no products. Yeah? So that before reaction thing, we're thinking about them being in separate flasks. You've got a solution of ethanoic acid and a solution of hydroxide ions, and until you mix those together, the reaction can't happen and the ethanoate can't be made. Yeah? Now, this, if you look at that number, that 4.94, hopefully, if you think about it for a second, that should be what you would expect. If you have a solution where the amount of the weak acid and the amount of the conjugate base are the same, then the pH is equal to the pKa. Yeah? In this case, we've added more base. And so you would expect that the solution should be more basic than it was when you started. Than it was if you had those amounts of acid and base being the same. Because it's a buffer, you wouldn't expect it to be much more basic, but you would expect it to be more basic. And so you'd expect the pH to be bigger than it was if those amounts were the same. Yeah? You see what I'm saying? And so this is a good check for you to make sure you've done the calculation right. Because it turns out that if you get those numbers around the other way, so you put the 0.8 on the top and the 1.2 on the bottom, this comes out as being negative 0.18. And so your pH of your buffer solution will be 4.56, no, 5.8, a smaller number. And so that would be telling you that compared to when you have equal amounts of each of the acid and the base, this solution is more acidic. Right? And that shouldn't make any sense. You see what I'm saying? If you add base to the solution, it should get more basic and the pH should get bigger. If you added a little bit of strong acid to the solution, that starts off having equal amounts of weak acid and conjugate base, then the solution should get more acidic and the pH should go down. And so this is another check to make sure that you've done the calculation right. Right? You can do all the math and you can plug numbers in, you can come up with some number, and your calculator says that it's 4.94, and you go, well, that must be right because my calculator said so. But it's always a good idea to take a step back and go, now, does this answer make sense? Has the pH changed in the correct way that I would expect for adding more base to it? Yeah? See what I'm saying? Okay. So that was question type number 2. And now we have question type number 3, the last one. So here we go. A buffer solution is prepared from 25 mils of 0.12 moles per litre benzoic acid, a new acid to be interesting, and 25 mils of 0.12 moles per litre sodium benzoate. And it tells you that the pKa for benzoic acid is 4.20. And so the question says calculate the pH change when 5 mils of 0.1 moles per litre HCl is added to this buffer solution. Right? So there's quite a lot in there. It's saying we've made a buffer solution from mixing certain reactants together, and now what we want to do is add some strong acid to that buffer solution and calculate the pH change that results from adding the strong acid. And so there's going to be there's going to be three things we have to do here, right? The first thing is going to be work out the pH of the buffer solution before we add the hydrochloric acid. So just work out the pH of the buffer solution itself. Then we have to work out the pH of the buffer solution after we've added the hydrochloric acid. And then thirdly, we have to work out the change in pH, right? We have to remember that little bit at the end because that's what the question wants. Not just working out the new pH, but working out the change in the pH. And so first of all, if we want to work out the pH of the buffer solution itself, then what we do is we look at the question and we see that this part of it, at least, is like the first question that we did. We're told we take a solution of our weak acid and a solution of its conjugate base, and we just mix those together. So if we can work out the amount of weak acid and the amount of conjugate base, we can put those numbers straight into our Henderson-Hasselbalch equation and work out the pH of the buffer. Yeah? And so again, I've kept the numbers nice and straightforward. The volumes are the same, the concentrations are the same, and so the amounts of the benzoic acid and the benzoate ion, the conjugate base, will be the same here. And so that means that the pH of our buffer is going to be what? 4.20, yeah? Because these amounts are the same, that means that the pH of our buffer solution will be equal to the pKa of our weak acid. Yeah? And so I'm probably going to spend a whole slide doing that. Next. Yep. But again, it's good to write this out. Do all your working. So the pH is equal to the pKa plus the log of the amount of benzoate over the amount of benzoic acid. And so it's 4.2 plus the log of 3 times 10 to the minus 3 over 3 times 10 to the minus 3, which equals 4.2. Yeah? And so that's the pH that we start with. Now what we want to do is we want to work out what the pH of that buffer solution changes to after we've added the small amount of hydrochloric acid. Yeah? And so the first question is, would you expect the pH to be bigger than 4.2 or smaller than 4.2? Who says bigger? Who says smaller? Well, that's more hands than bigger, at least. It should be smaller, right? We're adding acid to it. We're going to make the solution more acidic, and so the pH should go down by a little bit. Not a lot, but by a little bit. Yeah? And so to work out how much it goes down to, we'll do one of these tables, like we've been doing already, where we have a before reaction and an after reaction line. Now it's going to be a little bit different because before the reaction, we have a buffer solution. So we've got both the weak acid and the conjugate base together in one beaker, and then we have another little beaker which has got our hydrochloric acid in it. And so we want to work out the amounts of both of those things in here and the amount of strong acid in here before we mix them, and then we mix them, and then we work out the amounts of everything after the reaction's finished. Yeah? So the reaction that happens... Oh, hang on. Here's the reaction that happens. If we add hydrochloric acid, which remember we're going to... Hello? Yes? Oh, you were just stretching. Excellent. Good. Don't let the blood settle. If we add hydrochloric acid, then that's the same as adding H3O+. Yeah, because remember, HCl, strong acid, completely reacts with water to turn into H3O+. So the H3O plus will react with the base part of our buffer solution, the benzoate, and the products of that reaction will be benzoic acid and water. So that's the reaction that's going to happen. For us to work out all of our new amounts and our starting amounts, we've already got the amount of the benzoic acid and the amount of benzoate in our buffer solution. Now we just need to work out the amount of hydrochloric acid, which will be the same as the amount of H3O plus. Yeah? And so there that is across the top there. The amount of H3O plus is just equal to the concentration times the volume. And so it's 0.1 moles per litre times 5 mils, which is 0.005 litres. And so that comes out as being 5 times 10 to the minus 4 moles. Okay? So now we're going to do a table. We know the amounts of stuff in our buffer solution. We know the amount of strong acid that we're going to add. And so we can set up a table now, just like we've been doing, to work out the amounts of everything at the end of the reaction when we mix them together. When we have those amounts, we can put those back into our Henderson-Hasselbalch equation and calculate the new pH. Okay, so here comes the table. So now before the reaction, there's a bit more going on here, right? We've got an amount of benzoate that we worked out in the first part of our answer, 3 times 10 to the minus 3. We've got an amount of H3O plus, which we've just worked out, 5 times 10 to the minus 4. But now we also have an amount of benzoic acid, right? Because this time we're starting with a buffer solution which already has both the benzoate and the benzoic acid in it. So now we have 3 numbers here, okay? So that's before reaction. We have buffer in a beaker, we have acid in a beaker, the amounts of those in each of their 2 beakers. Now we tip one into the other, we mix it up, this reaction happens, everything finishes, and we work out the new amounts. Yeah? So when the reaction's done, the amount of H3O plus is, when the reaction's done, the amount of H3O plus is 0. Cool. It's all gone. The amount of benzoate, the conjugate base, will be 2.5 times 10 to the minus 3. Yep. The amount you started with minus the amount that reacted. And the amount that reacted is the same as the amount of H3O plus that reacted because of the 1-to-1 ratio. Yeah? We happy with this bit? So, if that amount of H3O plus reacts, which we're saying it does because at the end it's all gone, then because one of these reacts with one of these, it's a 1-to-1 ratio, 5 times 10 to the minus 4 moles of this reacts with 5 times 10 to the minus 4 moles of this. So the amount of this that will be left at the end will be the amount we started with minus the amount that reacted. So this number here is this number minus this number. Yeah?
It's always a limiting variable methods, right?
Yes. Yes. How far the reaction goes depends on the amount of the limiting reactant. Yes?
How come there's C6H5CO for the reaction?
Because we're starting with a buffer solution now, not with just a solution of a weak acid like we were before. Yeah? Okay, so every year I get to this point and I think I should change this, but this here, maybe in your notes, where it says 2.5 times 10 to the minus 3, if you're still not sure, write this. 3.0 times 10 to the minus 3 minus 5.0 times 10 to the negative 4 equals 2.5 times 10 to the negative 3. Yeah? Where this is the amount of C6H5COO minus initially, And this is the amount of C6H5COO minus that reacts. And so this is the amount of C6H5COO minus left over. Yeah? Okay? So that's that one. To work out the amount of the C6H5COOH that you have left at the end of the reaction, it's going to be the amount that you started with plus the amount that's made in the reaction, because it's a product of the reaction that happens, yeah? So the amount that you make of this will be the same as the amount of this that reacts. Because again, the balanced equation tells you that whenever one of these reacts, you make one of these. It's a 1-to-1 ratio. So if 5 times 10 to the minus 4 moles of this reacts, you must make 5 times 10 to the minus 4 moles of the acid as a product. And so when the reaction's finished, the amount that you're going to have is the amount that you started with plus the amount that's made in the reaction, which gives you a total of 3.5 times 10 to the minus 3 moles. Okay? So this number here goes down by 5 times 10 to the minus 4, and this one goes up because 5 times 10 to the minus 4 moles of this stuff gets turned into that. Yeah? So the number by which this one the reactant goes down is always going to be the same as the number by which the product goes up. And so then we have our two new amounts, right? So this is just the same as we did the previous time, but because the numbers are now a little bit less friendly, it looks a bit nastier. But it's exactly the same idea as we've already been doing, right? And like I say, in the tute and in the lab this afternoon, you get lots more practice at doing these because they're important. This is about as hard as we can ask you, but nonetheless, it's something we need you to be able to do. So once we've got these amounts now, we can just go back to here. We can plug in the numbers again. So the amount of benzoate is now 2.5 times 10 to the negative 3, and the amount of benzoic acid is now 3.5 times 10 to the minus 3. We put those numbers in. The pKa is still the same because it's a constant. And we do the math and we work out that the new pH is 4.05. And so then that's your new answer. And then, like I say, what you should do is you should take a step back and go, now it started off being 4.2 and now it's 4.05 when I added acid. Does that make sense? And hopefully the answer is yes. Right? You add some acid and the pH has gone down. Your solution is more acidic than it was by a little bit. And so that means that you've got the numbers around the right way in your calculation. And so we can say that that change is a small change. Right? You could say that it's gone down by 0.15. You could say that the delta pH is negative 0.15, however you wanted to say that. Right? But you would need to say that because that's what the question said at the start. It said, what is the change in the pH? So at the end, you would have to say the pH changes by 0.15 units. And it goes down by 0.15 units. Yeah? Now, of course, when we say a small change, small is one of these relative words. It's only small compared to something else. And so what I want to do on the next slide is just compare what would happen if we took the same amount of hydrochloric acid and added it to the same volume of pure water. Right? So instead of a buffer, adding it to pure water and see what the pH change would be then. Yeah? So 50 mils of pure water now, rather than 50 mils of a buffer solution. And we're going to add that same amount, 5 mils of 1 mole per litre hydrochloric acid to the water now, rather than the buffer solution. And so again, the amount of HCl is the same. So we have 5 mils of 5 mils of 0.1 molar HCl. So that's 5 times 10 to the negative 4 moles of H3O plus that is generated in that solution. And then we want to work out what the concentration of H3O plus is in that solution. And so now the concentration is just the amount divided by the volume. So this is the amount. We divide it by the volume now, and the volume is going to be what? 55 mils, says my friend in the front, because he's keeping up. Yeah? Because we have 50 mils of water, and then we've added 5 mils of acid to it. So the total volume now is 55 mils, or 0.055 litres. And if you do that, then you can work out that the concentration of the new solution is roughly 0.01 moles per litre. So if that's the concentration of the H3O plus in your solution, then the pH is just the negative log of that concentration. And so the negative log of 0.01 is 2. And so given that you started with a solution of pure water, which has a pH of 7, the change in the pH now is 5 pH units. It's gone from 7 to 2. And so you can see that that's a much bigger change than what you had with your buffer solution.